I have a history of UAVs that I'd like to share with you today. So when I first started working in the UAV industry, it was the early 1980s, and these were the aircraft that were being spoken about most. The Aquila was an artillery spotter aircraft that had horrible reliability problems and was eventually canceled after probably almost $1 billion US spent, and it never saw any real service. The Pioneer was much more successful. It actually flew, it saw a lot of service, but still had reliability problems. I have a little video that kind of shows a little bit about the challenges in the early days of UAVs. This one I was actually involved with. We got the launch to work pretty well, but we had difficult flight regimes at times. And we also had to land in a very confined airspace, and we were doing demonstrations of that didn't always go so well. This is a mishap that the Hunter had because of a failure, I think, with the navigation system. And the last one is the saddest of all. That's a mishap that the Global Hawk had, and that they actually had done everything perfect, but they had a termination device for the range safety, and someone at another range actually accidentally went on that frequency and terminated the flight of the Global Hawk. So even though you do everything right, sometimes it doesn't end up well for you in the unmanned world. Well, I actually worked pre-Predator. I know my biggest claim to fame is being involved with the Predator, but before the Predator, I worked for a company called Leading Systems, and this was an early aircraft called the Amber. It was a DARPA program in the mid-'80s, and that aircraft actually had 30 hours of endurance, and was really one of the groundbreaking aircraft for long endurance ISR. After that, I was involved with the Nat 750. This is the first aircraft that we at General Atomics actually sold to the general market. We sold it to Turkey in 1992, and that aircraft as well had endurance of about 40 hours. This is a slide I'd like to spend a little bit of time with, because I think the most important thing in a system is reliability. And if you can read that from the back, on the left, it's the number of Class A or B mishaps for every 100,000 hours. So at the number 200 there, that means you have accident every 500 hours. So what you can see is the Pioneer that I mentioned had radically improving safety record as it went along, as all the UAVs have. The Shadow, and it's much harder to have reliability in these smaller systems because you have to use smaller and smaller systems to control them and keep everything as lightweight as possible. But the Shadow, you see it coming down, and this chart was done in 2006, and since then the Shadow has now 1 million flight hours and has come down that curve quite a bit with an improved engine. And you can see the Hunter and the Global Hawk, but what I'm most proud about is those 3 lines near the bottom on the left, which is the Predator, the INAT, and the Reaper. And you can see that those airplanes, at their initial start, were even quite reliable, but really not reliable enough. The initial Predator had an accident every 3,000 hours, and eventually we got that airplane to have an accident only every 30,000 hours. This is the first Predator. The unique thing about that airplane is the bump in the nose, and that's because a satellite dish goes there. So it's the first airplane actually to be controlled through a satellite link. And we also did it through 2 different links. So the bump in the middle is a bulge where we had a UHF antenna, and we actually originally flew the airplane with a UHF satellite link, but the data rate that we could get back was extremely low, only 16 kilobits. It's hard to imagine that right now, but that's the way it was. So, the Predator was a groundbreaking aircraft, there's no doubt about it. Air and Space magazine came out and said that it was one of the top 10 aircraft to change the world. And why would that be? Well, as I mentioned, it was controlled via satellite. It also had the capability to talk to air traffic controllers beyond line of sight. It supported manned aircraft with laser designation, so it was the first one really involved in manned and unmanned teaming. It deployed precision ground weapons, and we actually even put a Stinger on it for an air-to-air capability. This is a video of the airplane in flight. That's a version that was after we took the UHF antenna off, so it doesn't have that bulge in the middle. It's a very stable platform, and one of the unique things about the design is that the bottom is the landing gears retracted, and you can see that the gimbal up there would have total 180-degree view of everything down below it without obstruction. So an area for our future growth for UAVs is going to be in the data links. Originally, all the data links were line of sight, and that meant that you really actually had to be able to see the airplane to control it. And not maybe with your naked eye, but the line of sight had to be there. And that really means that your limit is about 150 miles, and that's if you have no obstructions. With typical terrain in between the ground station and the airplane, you might only get 40 to 100 miles distance. Another way to improve the range that you can fly a UAV is to put a ground station forward. And if you put a ground station forward, you can actually fly the airplane out and have another ground station take control of it. And that allows you to actually have an effective distance from your original ground station of about 300 miles. So that's a good way to go. As I've mentioned, the Predator was the first one to be controlled by satellite. And the unique thing about this is that it just takes away that tether. So you're always kind of restricted. And with the satellite link, you can basically fly anywhere you want. And if you want to go to a different location, just fly over to that location. And we've routinely operated these airplanes about 500 to 1,000 miles away from where the ground station that originally launched the airplane was located. That's kind of an ugly airplane, but there's a lot to be proud of there. That's the very first airplane that was actually controlled by a satellite link. And it was an AT-750, and what we did, we got some money to put a satellite link in, and we didn't have room for it in the airplane, so we put it on top of the airplane. And so that pod on top has all the satellite link equipment and the dish that looked at the satellite, and it was never fielded or control the airplane through a satellite, which at the time was really quite groundbreaking. That flight was in 1993. Well, ground station is another area for growth. The ground station you see there is actually flown our fleet of aircraft for over 3 hours. And it isn't very much changed from 1994 when we first built the first Predator. The screens on the side have been added, but the main part of it is the same. And the screens on the side have been added for being able to chat to over the internet to whoever you want to communicate with, and to allow some security features, different information like threats to be on the side of it, but not be integrated into the ground station. So it works. It's a little bit keystroke intensive. It's a little bit engineering-ish. It has a lot of engineering data, and it's not really intuitive for the pilot. And you can see there's 2 of them there. Typically, a pilot's on one side and the sensor operator's on the other. This is our newest ground station. It's called the Block 50, or the Advanced Cockpit. And it's night and day difference in terms of the HMI, how the pilot interacts with the system. It's all graphical, so he knows immediately where in the airplane there might be a problem if there is one. You have a 360, not 360, about 135 degree view made through computer simulation, and then right in the middle of it, it blended in is a nose camera. The main screen in the middle and the bottom gives you a complete situational picture that has threats. It has a 3D map so you can see in all different aspects of where the airplane is. And it is on display at our booth today if you'd like to come by, and so you can actually fly the airplane there and get a full demonstration of it. This just shows the difference. For many, many years, we were on analog video, which is on the left there. And on the right is a higher definition digital EO camera. And it shows you the crispness and the difference that you get. In our data link early on, the payload would be analog. We'd have to convert it to digital to come down the satellite link, and we'd have to compress it, decompress it, convert it back to analog for dispersion to other elements beyond the ground station, and they would convert it back to digital for the display. And now the system goes digital right from the EOIR ball through the data link. It never gets converted, and it's digital from the ball to wherever it is displayed, essentially worldwide. Our newest product is the Predator XP. We have a model of that displayed also near our booth. And I'd like to tell you a little bit about this airplane. It's a blend of the Predator A, which has 2 million flight hours on it, and the Gray Eagle, which was designed in 2005 and first started operationally use in about 2008. And that one has 190,000 hours, I think more like about 200,000 now. And so this airplane is really the best of both of those. We've kept the Predator A aerodynamics because it's extremely efficient aerodynamically, but we've improved the propeller, we've improved the engine, we've improved the structure. It's with stronger composite materials than the original Predator A. But we've also added in the things from the Gray Eagle, which is a triple redundant avionics system with dual redundant flight controls, so that this is going to be a very, very reliable airplane. And we also have the capability to do automatic takeoff and land. And combining those two, we ended up with this Predator XP, which we're really quite excited about. I've got a few more slides on it. This is the basic specifications for the airplane. It can fly to about 25,000 feet. We just recently flew it for over 40 hours in endurance flight. We didn't have all the payloads on it and powered. So for a normal mission with everything on the airplane, we're confident of a 35-hour plus endurance. And this is some of the features. One of the big differences between the Predator A and this XP is the winglets that you probably have noticed. We do a lot with those winglets. We actually have antennas in there so that we can actually talk to air traffic control with an ARC-210 radio, and then we also have an AIS antenna so that we can basically do, basically it's like identify friend and foe with ships. You can identify ships, so it has a maritime capability. And one of the neat things I haven't mentioned yet about this Predator is that it has an EOIR ball, which almost all airplanes have, but this also at the same time carries the Link SAR radar. This is just a nice video, so I had to show it. We've been flying the airplane down in Yuma. We have over 200 hours now on the first initial airplane. The second one's coming off the line very soon. And as I mentioned, we had a good endurance flight. just a few weeks ago. So it looks a lot like a Predator, but it's completely redone inside with all the redundancies of our newer airplanes. I'd like to discuss payloads a little bit because really an airplane is just a truck, and it doesn't do anything for you unless you put unique systems on it. I won't dwell too much on the EO-IR system. It's a very capable system, but what makes this airplane unique is that it has a radar. And the radar gives you a capability to do wide area ISR. This is just a sample. It's a little bit crisper than that in reality, but you can get the general idea on the screen. On the left-hand side, you have towers for power lines. You have a irrigation canal, and you have pipelines on the right-hand side going away from that irrigation canal. It actually almost starts to look like a black and white image. This is an actual picture from a real mission that we did, and this is a river in the northern United States, and they had an early thaw, but then they had a real cold session at the same time and some tremendous rain. So they had ice in the river, and it was jamming up against this bridge, and they want to know how far back this ice was jamming up, and we were able to just fly right over this area, and you can clearly see in the river where the ice is that was threatening the bridge. So for those that aren't familiar, a radar can have several different modes and several different added capabilities versus EO-IR. With EO-IR, if you want to see with any resolution at all, you have a narrow field of view. With the radar, you can have that same resolution out to a greater distance. And so you can do what's called synthetic aperture radar strip map. And you can also use the radar in a mode where you're just looking for anything moving. That's called GMTI. So you can see moving targets. And we also have a capability with this airplane to see maritime moving targets, which a lot of these radars don't have that capability. We also call it MWAS, Maritime Wide Area Surveillance. And that allows you to do a maritime sweep and gives you a good maritime capability as well. So this is just a little bit of imagery on the top. It shows you just kind of a residential area strip map. And on the left is an EO image, and on the right is an IR image, fairly close up on that IR image. There's another image again with a strip map on top, EO image of a ship and of an IR image of a different ship. So I'll talk a little bit about future capabilities. One of the things that we found out is that once you have your airplane accepted as an airplane and not some radio-controlled toy, the Air Force and the armies of the world that have other airplanes that are flying want to interoperate with it. And so what we're putting on our aircraft is Link 16. And for those of you that aren't familiar, this is a way to exchange real-time tactical information among all the flying forces. And both with the Army and the Air Force, we've done a lot of different coordinated ops, actually laser designating for manned helicopters. And it's really opens up a whole new world when you think about the whole force and combining something that's unmanned with something that's manned. Where we're heading in the future is Ka-band SATCOM. It'll allow you to have a smaller antenna, more bandwidth, and the satellite constellation up there is a little bit crowded in the Ku and C-band, and so this will give you a whole nother band up there that will allow you to have more bandwidth. And there's also a bunch of new satellites coming on that are Ka-band. The last thing I'd like to talk about is sense and avoid, and that is something that's really mainly needed when you want to operate domestically, and you don't have another ability to separate traffic. So in the United States, this is a very big challenge for us. We can fly on ranges, and we have some beautiful ranges out in the West, but if you want to fly in the regular airspace, it's a real challenge, and they have something called see and be seen. And we want to go beyond that because we want to fly in weather with clouds and all that. So what we have is, what we put together is a multi-level capability where we have TCAS, which is, you know, the traffic collision and avoidance system, but that only works with cooperative aircraft. So if they're not cooperating, and if they don't have a TCAS system on their airplane, such as a balloon or some sort of other intruder, potentially even a airplane of someone bringing in illegal drugs or something like that, you still want to avoid that airplane. So we have a radar, which we call our due regard radar, that can actually see traffic out to about 10 miles. It allows the pilot plenty of time to evade that traffic, but if he, for whatever reason, doesn't do that, it can default into an automatic mode at the very end game and avoid the oncoming traffic itself. I don't have a slide on it, but one other area of growth I feel strongly about is the electronic spectrum capability of airplanes like this. So what you can do with an unmanned airplane is you can do jamming, you can do communication relay between different people on the ground, and you can actually pick up signals from maybe enemy forces with the airplane as well, with something, you know, like a SIGINT type payload. I think there's going to be a lot of growth in that area. It really gives the UAV a third dimension beyond the EOIR and the radar. So in summary, I'd like to say that I think the most important aspect of an airplane is reliability. And especially as the airplane gets larger, it's extremely important to have that airplane be reliable. I think ground control stations are going to be a big area of improvement, especially in the area of dissemination and processing of all the data that comes down from these payloads, automatic processing, 3D type processing. I think there's going to be a lot going on in the ground station area. I think radar is something that gives you that added capability, all weather. And the biggest challenge we're working on right now is just integration into the commercial airspace. So one day, it seems not that hard, but it is to be able to just file your flight plan and fly just like any airplane. And that's the goal we're working on. I don't know if I have time to take any questions, or should... Is there any questions that anybody has? Or? All right. Thank you very much.